Okay, so sample problem 16.5. You were going to find this on page 1131 in your book. And the problem statement here, we've got a cord is wrapped around a homogeneous disc, okay? And what that means is it's the same cross section and the same material throughout. It has a mass of 15 kilograms. We have a cord here. It's going to be pulled upward with a force of T, and that means tension in that cord of 180 newtons. So don't think torque, even though we're rotating around. I'm not crazy about that variable, but T is the tension in that cord as it's being pulled up. They want us to determine the angular acceleration around the center of the disc. So that's going to be alpha of the disc. They also want us to determine, the angular acceleration on the disc, and then also the acceleration of the cord itself, okay, of the cord. Oh, the acceleration. So the straight line acceleration. Sorry, I read that differently. So acceleration of the disc, and then also the angular acceleration of the disc and the the acceleration of the cord. So, what we're going to do is we're going to start off by creating a little diagram and putting our knowns and our unknowns. So this is sample problem 16.5. Okay. We're going to put our convention in the upper right-hand corner. And it gave us the radius of our disc was equal to 0.5 meters. Now, that is different than radius of gyration because they told us that this disc was homogeneous. And as I said, that means that it's the same cross section, same material. They are giving us the radius to the outer edge, if you would, the outer edge of the disc itself. Okay, so this is radius, not radius of gyration. They also told us that the mass of that disc is 15 kilograms. Okay. So now kind of using that same formatting that I did previous, instead of drawing the circle, we're on 16.5, Chris. Oh, sorry. I should do my finds over here. I'm going to find the angular acceleration of the disc. Okay. I'm going to find AY, AX, which is the acceleration of the center of our disc. Okay. And then the acceleration of the cord. So angular acceleration at the top, and then these are all straight line accelerations. The cord here. There we go. No, but we'll kind of see it at the end. We'll use those because there's a difference in the tension we're going to see in our diagram and the weight. So there is a resultant force, which is there's going to be an acceleration. And then all that it means then is that wherever it's held, it has to be able to resist that. Okay. All right, so we're going to draw our diagram and we are going to going like this. And this is going to be my G, and I'm going to look at the left-hand side because I've got my tension of 180 newtons in that cord. Okay, and this is G. And the distance here is 0.5 meters to the end. And that's going to be equal to, and we're going to take center of G here. And then we're going to have so we're going to have the straight line accelerations in both directions, AX and AY, and we'll solve for them and we'll kind of see how that works out. And then we're going to have our moment of inertia multiplied by the angular acceleration for our angular momentum. Now, reminder here. We are given the radius this time, not radius of gyration, as I just stated. So that means that our moment of inertia of our disk is going to be 1/2 mr squared is going to be the equation. Okay, so it's radius this time, not radius of gyration. And that'll come in handy a little bit later. I'm just going to kind of put this as a note up here where I is equal to mr squared, because we'll refer back to that. And again, you might, because we're given the radius and this is a homogeneous disk. Sorry, I forgot the 1/2. Got to get it right in order to get the right answer. Okay, so what we're gonna do is we're gonna kind of look at this and we're gonna go through our 3 equations. Some of the forces in the x equal m times ax, some of the forces in the y, m times ay, and then our sum our moments. So we'll start with sum of the forces in the x equals max. Now, you'll notice that there are no forces. I got another force, didn't I? Sorry. What did I forget on my left-hand side here? The weight of our pulley or our disc. This is going to be W, which we don't know the value of yet. We'll be calculating that, so please add that. So we are going to sum our forces in the x direction equal to max. And you're going to notice here we don't have any forces in the x direction. So that means that's going to be 0. So 0 is equal to max. So solving for our acceleration here in the x direction, we're going to say that that is equal to 0. Okay, so that takes care of our ax. Actually, I'm going to change my cloud to a box because that is a final answer. I put clouds around intermittent ones that we're going to go back to. Then we're going to do the sum of the forces in the y. And that's going to be our MAY. Now, this time we do have forces in the y direction, right? So we're going to have a positive 180 newtons. And we have a minus W. We know W is equal to mass times gravity, right? So we know the mass is 15 times 9.81. And that's going to be equal to the mass times the acceleration. Oops, I'm sorry, the mass again, which is 15 times the acceleration y. So solving for the acceleration at y, okay, we're going to divide both sides by 15. So we end up getting, solving, ay should be equal to, make sure you check your values here, 2.19, and this would be meters per second squared. Is that what you got? Mm-hmm. So that's another one of our values taken care of. Here we go. All right, and then the last one that we're going to do is because we have a rotation around that center of G, we're going to do our summer moments around G, okay, over on this side, and then around our inertia. So sum our moments around G going to be equal to I alpha, and you could do a plus MA D perpendicular, but you're going to notice that we don't have offset distances to where the acceleration is occurring, right? So if we sum around G here, our accelerations are going through, there's no perpendicular distance. So that goes to 0. Okay, just if you're wondering why we're not adding that portion in for this. Okay, so over on the left-hand side, we're going to sum our moments around G. So that means we're going to put our finger on G and we're going to push in the direction of any offset forces. So T, which is 180, times its perpendicular distance of 0.5. And then you're going to notice that it's going to go in a clockwise direction. So that's going to be a minus out front. It's going to be equal to, now again, we're rotating around G. The direction that we assumed that this is going, that the book assumed, I'm taking the same direction that they did, is going to be in a clockwise direction. So this is going to be positive on the right-hand side, so we don't have to put a negative in front. But now we have to put our moment of inertia. We know that that moment of inertia is 1/2 mr squared. So we're going to put 0.5 out front times 15, which is the mass, times the radius squared, which is 0.5 meters squared. Okay. And that is the moment of inertia. So this is I. And then we're going to multiply that by alpha. Okay. All right. So now alpha is our only unknown here. So we're going to be solving for alpha. So you should get -90 divided by, if we multiply these together, this is going to be 1.875. It's going to be equal to our alpha. Actually, yep. And then we're going to have a negative 48 radians per second squared is equal to alpha. Now, this is not slowing down because we're pulling on that. This is going to actually start speeding up, right? So what does that negative mean to us? We look at the direction up here. What does that mean to us? Exactly. And that makes sense because if we take we weren't given our weight, right? But if we look here, if we're summing around G, this is going to rotate this way, right? So this has to rotate this way. That confused me a little bit when I went through this problem the first time. Like, why are they going in that opposite direction? Because naturally I was picturing it going the opposite way. But I believe that they did it as a point of, again, remember, if you have your convention up here and you follow your convention, these final answers let you know if you were right or not on the direction. And in this case, we got a negative value, so we were incorrect on the direction. So we just make this positive and we say this is our final answer. But instead of going in a counterclockwise direction, it's going to go in a clockwise direction. And then we're going to change the direction up here to go this way. So make sure that you change it in both places. You don't have to redo the math, but you want to reflect the correct direction of the angular acceleration. Okay. So that is our third variable solved for. Now we just need the acceleration of the chord. Okay, the acceleration of the chord. So now what we're going to do is I like the illustration that they have here. So down here at the bottom, they have the illustration of just looking at the accelerations again. So I'm going to mimic this very same thing that they have here. So we know that, and I'm just going to draw coming from G here. Okay, this is our G. We know that we have the chord going up, but just showing the acceleration of the chord, this would be the straight line acceleration of the chord. Okay. We know that now, based on what we just saw, or what we just calculated, that our alpha is going in a clockwise direction. Our radius is right here, and we know that to be 0.5 meters. And we also know we have a y-directed acceleration on G as a y, right? This value we know to be 2.19 meters per second squared. The angular acceleration we know to be 48 radians per second squared. Okay. And now we need to find the acceleration of that chord then. Okay. Now the acceleration of the chord is going to be equal to the acceleration in the y plus the acceleration of A sub G, or the one in relationship to A and G. Now, this is like a tangential component out here, like we saw earlier. So we know that AY is 2.19, and this is going to be the radius, okay, times alpha. So that would be equal to 2.19 plus 0.5 times 48. Okay, so that's our alpha from up here. So the acceleration of our chord then is going to be equal to, if you multiply these out, you should get 26.2 meters per second squared going up. Yeah, because that would be 24 plus 2.19, so 26.2. And that's the last acceleration that we have. That one. Okay. So now this is the last sample problem that we have for chapter 16. So what this does is it sets you up to be able to now do the application problems that are going to be assigned for the entire module. There's going to be some from chapter 12 and then some from chapter 16 as well. So I am going to stop the recording here, and then we'll look at some of these application problems and make sure that you know what you're going to be doing.